This week we're going to be learning about the gas laws, and in this video we'll cover 5 different gas laws which give us 5 equations we can use to calculate the values such as the pressure and volume of a gas. So before we can do that, we're going to need to discuss what pressure means when we're talking about a gas, so that you can understand all of the relationships I'm about to explain. So if you have a container with gas particles inside of it, gases have a lot of kinetic energy, and that's why these particles are not close together. So they're moving around quickly inside of this container, and eventually when you're moving in a container, you're going to hit the wall of the container and have to bounce back the other direction. So all of these particles are doing that at the same time, and the walls of the container are feeling that force from the gas hitting the walls. And that is what the pressure is. So if the gas particles move faster, that means they hit the walls more frequently, and the pressure would be higher based on the rate of the gas particles crashing into the walls. So that's going to lead us into the first gas law, which we'll discuss today, which is Gay-Lussac's gas law, and it relates pressure and temperature of a gas. And I'm going to use these boxes that I have here to be able to hopefully explain why these relationships are the way they are. So if in the first box here I had 4 particles of a gas, and they're moving at a certain rate and hitting the walls of the container at some certain rate. Now they might be moving with, we can use an arrow to represent how fast they're moving at this temperature. So this is at T1. Okay, so my pressure will be some amount at T1. Now, let's move to the next box. This is after we have increased our temperature. So T2 is higher than T1. Now, when we increase temperature, that means the overall kinetic energy of the particles is higher. So they should be moving faster. So I'm going to draw bigger arrows to represent the speed of these particles. Okay, so since these are moving faster, T1 is smaller than T2, and that means that our pressure from T1 is going to be lower than our pressure from T2. So P2 will also be greater than P1, just like T2 is greater than T1. So if our pressure increases, our temperature also increases. Okay, so the equation that we can use for this should be the equation we can use for this we'll get in just a second. So that means if we increase our pressure or our temperature, it doesn't really matter which one we're increasing. Actually, you know what, I'll stick with temperature because that's what I was explaining in the graph or in the images above. So if we increase our temperature to the right, our pressure also increases. So the graph would look like this. And that means that our variables are directly proportional to one another. And to be able to write this equation, we have the pressure in the first box, or pressure 1, divided by temperature 1 equals pressure 2 divided by temperature 2. So if you were reading a question and you could identify what was the initial temperature, final temperature, initial pressure, final pressure, you could plug those into the correct locations in the equation. Alright, next we're going to move on to Boyle's law. So this relates pressure and volume. So if I have a certain volume of a box, my particles will have to move a lot farther to hit the wall of the container in this box than they will in this box. So assuming they're at the same temperature and moving with the same kinetic energy, same speed, then they're going to hit the walls a lot less frequently in the bigger volume. So if we have a bigger volume, V1 is greater than V2, our pressure will be lower in the container where they have more space because it takes longer to get to the other side. So P1 will be smaller than P2. This means that they are inversely correlated. So if my volume is increasing, my pressure must be decreasing. So this is what the graph would look like for that. So the formula we have for Boyle's law is P1 V1 equals P2 V2. Okay. Then finally we move on to Charles' law, volume and temperature. So if we were to start with a smaller volume here and a certain temperature, and maybe it's easier to think about it with temperature. If we have a lower temperature here and we increase the temperature, those gas particles can move farther more quickly, and that causes flexible containers such as a balloon to expand. And you would see this if you were to put a balloon in ice. It would shrink a little bit versus putting it in a really warm environment. It will grow bigger. If we increase the volume, that gas has to move faster to be able to maintain the same pressure. And this is why if we're holding pressure constant, the volume would be larger for a higher temperature. Okay, so T2 is greater than T1, and our V1 is smaller than our, it should be V2. Okay, so in this graph, we will have also the same thing as before. Wait, V1 less than, temperature 1 less than. Yes, okay. So in this one, it's going to be similar to how the variables were related in Gay-Lussac's law. If our temperature is increasing, then our volume is also increasing. Okay? So the law here would be P1, nope, pressure's not involved. V1 divided by T1 equals V2 divided by T2. And our pressure is held constant in this law. Okay. So we could use some different problems and identify our variables, and I just want to make sure we can do that quickly. So there are some different variables for pressure, some different units that we use for pressure. Some of those could be ATM, it could be ATM, millimeters of mercury, or mmHg. We could see Pascal or kilopascal. These are some different units we could see for pressure. And we know temperature and volume pretty well. We're familiar with those variables. So in the first problem here, we have 4.35 liters. Liters has to be a volume. Okay, so we also have another liters later in the question, so this also has to be a volume. And we have an ATM here, so because that's a unit of pressure, that must be a pressure. And then we get to this point where it's asking us what pressure. So that means we have an unknown pressure. So we need to know which volume goes with which pressure for our initial gas, and then which volume goes with our unknown pressure for our final gas. So what's logical is to read the phrase, 4.35 liters of a gas is at 1.16 ATM. So that means this must be my pressure 1 and my volume 1. So those two must go together because they're talking about the same gas at the same time. Now, we increase the volume to 9.3. That must be our second volume. And at that point, we want to find our pressure. Okay. So we can plug these into the equation and be able to calculate. So if I have P times V is the format for this equation, I'll have 1.16 times 4.35 equals P2 times my 9.3. So you could solve like we have been, where you divide on both sides by this 9.3 because we need to isolate our P2, and you multiply these two, then divide by 9.3, and we would get our answer for P2. We could go about the same thing for each of these equations, or each of these problems. If we have 4.73 liters, that must be a volume. If we have 35 degrees Celsius, that must be a temperature. And then it's asking what the volume would be, so that must be our unknown, at the standard temperature. And it tells us right here that standard temperature is 273. So to be able to have our temperature in the same unit, we would have to convert this one. So we would take our T1 here, and we would add 273 to our Celsius value to be able to get it into Kelvin. So our Kelvin temperature for the T1 must be 308 Kelvin. That's our T1. The T2 is this 273 right here. And we are using this volume right here, since it's in the same container, the same gas as the 35 degrees Celsius, this must be our V1. So we could use the equation that was V1 over T1 equals V2 over T2, and we would be solving for our V2. So plug in and we can solve easily. Now, since this is in the denominator on the right side, we're going to have to multiply it on both sides, so we would have T2 over here in the numerator. Okay. Last question. We've got liters, we've got Celsius, and we have millimeters of mercury. Now, all that it says right here is that we're changing our temperature to standard conditions, which means we're changing our temperature to 273, and it's asking us for our new pressure. So this one's a little bit trickier. We're going to be changing the temperature, so we know for sure temperature is going to be involved. Okay, so we're going to have T1 was our 32, and T2 is this 273. We're going to have to convert this one to Kelvin, so let's add 273. You're always going to convert your temperatures to Kelvin, so this should be 305 Kelvin. Okay, and then we have 273 for the other one. Then it's asking us what the new pressure is. So since it gave us an original pressure and it's asking us for the new pressure, our other variable must be pressure. Now we can ignore volume. It's not that important in this question because it's not changing. It's being held constant. So our millimeters of mercury, this will be our pressure 1, and the new pressures are unknown, our pressure 2. So we must be using the P1 over T1 equals P2 over T2 equation. And the thing we're solving for is our P2. So once again, the temperature needs to be multiplied on both sides. So T2 would move over here to the numerator when you multiply it on both sides, and it would cancel out on the right side. You plug in your values and you solve, and that would give you your final pressure. Okay. In a few moments, I'm going to be telling you about the other two gas laws, which are a little bit more complex because they have at least 3 variables, and we're going to wait until the next video for that so we can hopefully focus and cover everything all at once. So we'll look at the combined gas law and ideal gas law in the next video.